From example 2.1, part 3, we have seen how a regression line can be used to estimate the value of one of the two variables for a set of bivariate data, given a value of the other variable. However, from example 3.4, part 2, note that even if the bivariate data demonstrates a linear relationship, adding more data points may show a different relationship between the two variables altogether. Hence, it is risky to use the regression line to estimate the value of x for a value of y that lies outside the range of data values of y, or to estimate the value of y for a value of x that lies outside the range of data values of x. Therefore, to determine if an estimate or predicted value obtained from a regression line is reliable, we consider the following questions. 1. Does the given value lie in a range of values of the dataset? If the answer is no, we can immediately conclude that the estimate is not reliable. If the answer is yes, we consider the next question. 2. Is the absolute value of r close to 1? If the answer is yes, then this means the linear model is a good fit for the data, and therefore we can conclude that the estimate is reliable. However, if the answer is no, then a linear model may not be a good fit for the data, and hence we conclude that the estimate is not reliable. The process of carrying out estimation from within the data range is known as interpolation, while the process of carrying out estimation from beyond the data range is known as extrapolation. As mentioned in the previous slide, an estimate that is obtained by using extrapolation is not reliable. Let us now look at an example that illustrates the concepts that have been discussed thus far. Refer to example 4.1 in your lecture notes. An instrument is used to measure the amount of vitamin C in a given volume of liquid. It is standardized by using it on 7 specimen solutions containing known amounts of vitamin C, X, in micrograms per milliliters. The reading on the instrument is denoted by Y. Corresponding values of X and Y are given in the table, as shown on the screen. Part 1. Find R, the product moment correlation coefficient between X and Y. Part 2. Using a suitable regression line, estimate the value of X when Y equals 3.5. Part 3. Comment on the reliability of this estimate that you have obtained in Part 2. For Part 1, R equals -0.999. For Part 2, since the reading on the instrument depends on the amount of vitamin C in the solution, we should use the Y on X line, even though we are estimating X from a given value of Y. The equation of the Y on X regression line is given by Y equals -0.00793557 X plus 7.0771. Recall from example 2.1, since we are using the regression line to carry out estimation in this case, we need to include more significant figures in the coefficients in the equation of the regression line. Therefore, by using this regression line, the estimated value of X is 451. Correct 3 significant figures. For Part 3, note that the given value of Y, which is 3.5, lies in the data range for Y, the closed interval 1.44, 6.26. Also, the value of R, -0.999, has an absolute value that is very close to 1, which means that the strength of the linear relationship between the two variables is high. Therefore, we can conclude that the estimated value is reliable. Note that what is important here is that the given value, which is Y in this case, must lie in the data range. We do not decide the reliability of the estimate by considering whether the estimated value lies in the data range or not. Let us now consider another example that illustrates the concept of the reliability of estimate obtained from a regression line. Refer to example 4.2 in your lecture notes. An anemometer is used to estimate wind speed by observing the rotational speed of its vanes. This speed is converted to wind speed by means of an equation obtained from calibrating the instrument in a wind tunnel. In this calibration process, the wind speed is fixed precisely, and the resulting anemometer speed is noted. For a particular anemometer, this process produced the set of data as shown on the screen. Part A. Obtain the equation of the estimated least squares regression line of R on S, and the line of S on R. Part B. If the actual wind speed is 1.65 meters per second, use an appropriate regression line to estimate the rotational speed of the anemometer. Part C. Demonstrate, using the above regression line as an example, that it is unwise to extrapolate beyond the range of the data. For Part A, the R on S line is given by R equals negative 90.8 plus 11.6 S, and the as on R line is given by S equals 0.78772 plus 0.008556 R. For Part B, since the wind speed is fixed precisely, it is the independent variable. Hence we should use the R on S line. Therefore, when f equals 1.65, the estimated value of R is 100.6 revolutions per minute. For Part C, when f equals 0, the estimated value of R is negative 90.8 revolutions per minute. In other words, the initial anemometer speed is negative, which is impossible. Thus, it is unwise to extrapolate beyond the data range, since clearly, a linear model is not a sensible one for values of S that are close to 0.